This is the high bridge. Hey, everybody likes this. Is one. Everybody gets that. So I was talking about bad juju bridges. The high bridge is a good juju bridge. It's got good karma. I've never had nothing but good luck on this bridge. I've lost a few cameras to it. But you know what? One thing I remember distinctly about this is that we did it with a snooper truck. We did an inspection of a snooper truck. This is a underbody or underbridge inspection truck. It's got this big multi-arm thing that goes up underneath, and you can get up into all the nooks and crannies and look at them from above. And you know, it's kind of precarious. And some of these areas, you know, there's a lot of steel coming in together, there's a lot of stuff, and we saw something on one of the bearings underneath the girders at the top of the tower there, and we said, that looks funny, we should check that out. And so we did all this stuff to get this piece of equipment in there. It took us about 15-20 minutes in there. I had to take my hard hat off because I couldn't get my hard hat into the spot I needed like that. And I get my hard hat off, I stick my head in there, and I'm looking at like 700 wasps staring at my face. And thankfully, it was October, it was like 40 degrees out, and they were looking at me and they're like, if it was 20 degrees warmer, you'd be dead. But that's why I say it's a good juju bridge. There's things that could go so wrong on this bridge, and it seems like whenever you're out there, things just go well. And so thankfully, I've always had a good experience with this bridge. Part of my work involved with this, I've inspected it a few times, like I said, in a super truck, and then we've done steel repairs to it. The company's done steel repairs to it, and we've designed the steel repairs. This is the photos of the steel repairs, and this is on the tops of the big arches, and where the deck ties rest on the top of the steel arch, that plate of steel is wearing out, and so we were tasked with replacing it. And we have a high rail mounted crane. It's a 30-ton lattice boom crane that does this. This is not a rail crane. And you'll notice on the front of that thing, when you're 190 feet in the air, and we'd have to take a track panel out. You can see right now they're picking the track panel out. When you're 190 feet in the air and you're going to back, you know, 30, 40-ton crane back to an opening, a 50-foot gap in the deck, 190 feet up in the air, you really want to make sure that that crane's going to stop. You know, this is a 1966 link belt. She's nice, but you know, if the brakes don't work, it's going to end badly. So that thing you see hanging out the front, one of the engineers who designed a giant restraint system for it, and they'd actually hook cables up, those big springs, and they'd stop short, anchor that down to the bridge. They had a couple of spots in the steel that they'd anchor that to, and then the crane would go down and stop. If it didn't stop, the two cables would engage those springs, and that would stop the crane. And so that's, you don't want to have a mishap that high up in the air. We never used the springs, never even compressed them once, so once again, good juju. So now you're seeing the top of the high bridge, and this is where the track rests on top of those steel arches, and the plate that they're prying out of the way is basically the top, what we call the top of the cord here, and lots of places that it corroded through. The bridge is actually in remarkably good shape. The steel in the bridge is in remarkably good shape, but this is a part of the bridge that gets a lot of wear and tear being right underneath the track. So the bridge engineers in here, the locomotive engineers that have been across this bridge, and everybody that's ridden across, everybody has the story of looking out the side of the locomotive, etc. She is a pretty stout bridge, and but we're doing a little bit of these repairs. And in 12 hours, once again, to keep the dispatchers happy and make sure we don't delay any trains, in 12 hours, they would remove all the rivets. There's 350 rivets in each plate, so 700 rivets. They bust the heads off the rivets, punch them out, push the plates off to the side, pick up the new plates that go in place, put in 350 bolts, 700 bolts, tighten them all up, and then put the deck back on top of it. And repeated this time 7 times per span for 4.5 spans. This work, actually, the Sioux had started before they had sold it to the WC. The WC didn't do anything, and then the CN did the work afterwards. The other part of this bridge, other than the top, is the bottom, the pedestals. And we did work on cleaning up and repairing the concrete in the pedestals. If you go up there on a boat now, a lot of these look a lot nicer than they used to. The pedestals actually are not in that bad a shape. Really did the concrete was to keep it all stable so it didn't get any worse. But one of the things I think that's deceiving about the sheer magnitude of this bridge is for you to see a picture of a pedestal like this without a lot of context. You know, a lot of these things are about as high as this tripod. You go up, okay, here's a concrete pedestal. We're going to go and look at the bearing on top of this concrete pedestal. These are like 30 feet tall. They're the size of a house, the base of those arches. So if you've been by the bridge on a boat, you've seen them up close. If you've been up on the train and looked down, they look like nothing. But they're quite a bit. And we did this Batman style. You can see there's one of my engineers I work with. He's just about ready to get it set up for it. You can see we have our fault protection on. And what we would do is that he would throw the rope up across one of the braces. And then, I was a little bit bigger back then, but anyways, I was the dead man. He'd clip that off the back of me, I'd squat down real low, and then he'd use that rope, this basically Batman style, up the back of that concrete pedestal to get to the top. And when he got to the top, he'd tie off the rope, and then I could climb up after him. And then we repeat the process on the way down. There was only one spot on the back side of one pedestal was the only place we could really do that. Every other face was too steep, but the back side of basically the southern pedestal was sloped enough that we could make it up there. And then once we got up, we'd climb across the bracing to the other side and look at the other bearings. Once again, did this several times, never had a mishap. So it's a good juju bridge. I've always liked the big bridge up there. And it's in good shape. So just a parting shot. As we head back to the end of the day, there really is, it's one of those bridges that you really can't get to the bottom without a boat. You can't get from the bottom or the top to the bottom very easily. All right. So any questions on those bridges? All right. We still got a long time till another bridge, train on a bridge picture, so I apologize for that. We're several slides out. So, anyways. I wanted to touch base on a few bridges that I found kind of interesting on the Soo Line, noteworthy bridges. And this one seems like the least exciting, but I think it's probably worth some merit. Or you know what? I apologize. I'm not quite to that same. I'm just going to get some general impressions about railroad bridges on the Soo. So if you model Soo Line, or if you're just curious about Soo Line railroad bridges, every railroad, there's a Railway Engineering Association that tells you how you're supposed to design railroad bridges. But every railroad kind of had its own way of doing things. And particularly with certain types of timber bridges, they had their own styles, which is their standard bridge. And the Soo Line was no different. The Soo Line had a way that it dealt with its bridges. And I've inspected bridges that, like I said, were former Chicago Northwestern, former Milwaukee Road, New York Central, Pennsylvania, Rock Island, Southern Pacific. They all had their own little kind of character. And the Soo Line is as well. Often there's some things that when I see a bridge, I can say, yeah, you know what, I think this is a Soo Line bridge. And so one thing that I would say about the Soo Line is that their timber bridges were pretty well built. Chicago Northwestern, I think we like to call it the cheap and nothing wasted, but anyways, they built a pretty, I know if there's CNW fans out here, I apologize, but they built a pretty spindly, cheap timber bridge. And if you go down south, like the Southern and stuff like that, they built some really spindly little timber bridges. And the Rock Island too. But anyways, I'm not going to trash every railroad I don't like. But the Soo, and I think it's interesting as a bridge engineer, I think it's interesting, the Soo Line and the Milwaukee Road built very similar timber bridges towards the end. It was almost the exact same plan, the same weight of timber, size of timbers, etc. And I find it interesting that those two ended up being the merger partners. It's almost like the railroad bridge engineers planned it, like, oh, yeah, good, now we can build the same bridge on that railroad as well. So, but yeah, it's very heavily built, well-built timber bridges, and they have a lot of them obviously in the Dakotas, but elsewhere in the system. So that's, I can usually see if I see a bridge, if it's not a Milwaukee bridge, it's a Soo bridge, and it's pretty well built. Another thing about the Soo Line is it didn't like bridges, and I have to give them credit for this. They thought the best bridge was no bridge, and so they filled a lot of bridges. And so what you're seeing here is a photo or a photocopy out of the Red Book for one of the wheat lines. So they had this book. It was basically like the roadmaster's kind of record of what we did on the railroad about bridges. And so this shows a bridge just out by Dahlen, just outside of Fordville, bridge 396.13, I believe. And this little bit on the bottom, right at the fold, there's like maybe what looks like about 3-4 inches. That's all the bridge that's left. That's what you see in the photo. Several hundred, if not 1,000 feet each way, they had a big giant timber trestle there and they filled the whole thing in. And this is not the only one that's out there. Around Fordville, there's 2 or 3 bridges like this where they filled in massive timber trestles. And they filled in a lot of bridges. If you flip through this red book, there was just lots of bridges that were built when the line was open. And my old friend, the Cheap and Nothing Waste of the CNW, I looked at what is now the RCP&E that goes across the Dakotas. Basically the same location, the old DME that runs from, let's say, Pierre to Rapid City, which basically parallels this the next state down. There's probably across South Dakota, the CNW probably had 700 bridges. Across North Dakota on the wheat line, I think they had like 75. So literally they filled as much as they could. And God bless them, because they filled them back in a time when you didn't need a permit to fill every one of them. Nobody worried about wetlands. So it made my life a lot easier. And another thing it tells me is that if I'm on a Sioux line and there's a bridge there's got to be a bridge there. It's not like, well, we just didn't want to put a bridge in. It's like this is going to flood and you have to have a bridge there. Now, their timber was pretty heavy. The steel on the Sioux, a little bit more workaday. I'd like to say they bought the Dodge with the steel bridges, or maybe the Chevy or whatever. It was not the top of the line Cadillac kind of bridges that they put out there for railroad bridges. And this is where they probably diverged from the Milwaukee Road. The Milwaukee Road would build much heavier steel bridges. Their steel bridges were perfectly functional, but were definitely on the lighter side of things. And so things like the bracing up above is a little bit lighter. Just the components all together are just very simple and straightforward. So they did not build really fancy steel bridges, unlike some other railroads. Another thing that they could have worked on is foundation design. And I kind of point this out. A lot of my interactions with Sioux Line Railroad bridges is because they've been sinking into the ground. And this is, if you look at that pedestal, this is a concrete pedestal with a steel tower resting on top of it. You notice that the steel tower is all the way off in one quarter. And it has a big stack of plates on top of it. Well, that plate is supposed to be centered in there. In fact, you can kind of see an old outline of where it was. Over the years, that foundation has sunk down like 6-8 inches and shifted sideways about a couple feet. And this is not the only Sioux Line Railroad bridge I've seen this on. If somebody took me blindfolded to a bridge and I showed up at it and I saw a pedestal look like this, and then where the bridge ends at the end, where we call the back wall sits up, if it's all chipped out because the girder is, the abutment's settling in the girder, I'd be like, I wonder if this is a Sioux Line bridge. So they just didn't quite put enough piles underneath the steel and concrete ones, and it's still kind of a little bit of a challenge. Here's another situation where you see this is settled like about 8-9 inches since it was built. Not something that's like an immediate problem, but it's just, that's something that kind of a Sioux Line thing. All right, now this was a segment I thought I was on before, I apologize. Just a few bridges of note. And this is a 581.49, so that bridge that we saw that was all swayed in the flood. And I think this bridge is important because it was built in 1990, and it's probably one of the last, definitely like on a Class 1 railroad, it's one of the last all-timber trestles that was built. We drove new timber piles, and it built an all-timber trestle. Today we built bridges primarily out of steel and concrete, steel H-pile, concrete spans, but this was built all out of timber. Back in 1990, which is much later in the game. Most of that ended in the 80s, and even most railroads really stopped in the 70s building new timber bridges. So like I said, it's got to be amongst the last in the U.S. and probably the last brand new timber bridge that was built for Class 1 in the U.S. Here's Oslo. I do think it's a unique bridge, and mainly it's because of that timber drum pier in the center. Most of these swing bridges you'll see, they have stone, concrete, drum piers, because there's a lot of force when that thing spins around to keep it stable and not tipping over. And on top of that, this sits in a river that's full of massive ice. It has huge floods, as we see in the photos. So the fact that they have an all-timber drum pier on this bridge, and it remains to this day, is really kind of outstanding. And then it's fully framed. And it's going to stay there until, for the most of the time being. It does need a massive icebreaker. One of the things I had to design those icebreakers to keep the ice from hitting it. And to get an idea of the force from that, if we could turn the icebreaker on its side, and just kind of hang it on its side, you could hang 3 loaded rail cars from the top of it. And that's how much force it could deal with the ice hitting it. It's in the millions and millions of foot-pounds of force when the ice slams into these icebreakers. And that icebreaker, you can see there, they're 32 foot tall. They have hundreds of thousands of pounds of concrete and stone inside of them, and they will move 8 or 9 inches when they get hit by the sheets of ice coming down that river. So to have an all-timber pier sitting in that same place, it just boggles my mind. But hopefully, thanks to Nickel, hopefully it's doing okay. There's another bridge I've worked on, and this is where I might have to duck down and get out of the way for whatever tomatoes are left over from the salad earlier. So this bridge is up on the Dresser line, which is the Dresser sub on the CN now, and near Osceola. We cross the St. Croix River, so this is a low crossing, old swing span. And there's a tourist road that runs on this. I've seen lots of tourist photos. The folks that like taking photos, you probably noticed a few years ago, they took all this nice stonework and covered it in concrete. And I'll admit right now, I'm the guy that covered it in concrete. Now, in all truth, what it was is that a canoeer going down the river saw a chunk of that bridge fall into the river, called the railroad up and said, there's a problem, and the railroad agreed, and the concrete was kind of needed there so that the rest of it didn't fall in the river the same way. But as part of the process of encasing these in concrete to stabilize them, we had to do a historical review of the structure. And one thing I thought was interesting, this is what the Mead and Hunt came up with, is that there was an article in the Osceola Sun from 1930 that talks about that as they worked from Turtle Lake to Osceola and they worked the other direction, they met up at the bridge and they drove the final spike at the bridge. So I don't know if this is the final spike on the Sioux line, but it would have been pretty close to one of the final spikes. This is, if there was a golden spike for the Sioux line, this is the bridge that it occurred at, which seems like a pretty rough spot to take a photo or something, so maybe that's why we don't see photos of it. But nonetheless, according to at least the 1930 paper, this is where they closed up a gap in the railroad, which makes sense because the bridge was probably the last and most difficult thing to build. And then, of course, we all talk about this Bridge 181.93 for us railroad bridge guys, but obviously the big bridge up in the Sioux. And the thing that's neat about this is that it has basically an example of every type of movable bridges that bridge engineers came up with. There's a swing span in it, it's got a lift span in it, that's what we're looking at right here. It has a bascule span in it, and it also has a double leaf bascule span, which, so if you look at bascule span is basically a hinge. It comes up, goes up and down like that. You see lots of railroad bascule spans. They're all mostly all single leaf bascule spans, which means they have one leaf that comes up, one span goes up 90-degree angle, opens up the waterway. The span just beyond the one we're looking at there actually comes together and goes up like this, just like the bridges you see in Chicago. But the bridges in Chicago carry, well, the L, but that's not much, but they mostly carry automobiles. Train loads are so much higher, and that span is much, much longer too. So it's very unique in the fact that it's a double leaf bascule truss bridge. So if you're ever up there taking the Sioux tour and you go underneath that one, it's got two sections swung up. Understand you're looking at one of the few examples of that type of bridge in the entire world. And then of course the Somerset Bridge. One thing that's neat about Somerset Bridge, I think is an interesting aspect, is it has a structural feature on it that the middle span, right above the center of those big arches, the top chord, those things that we were repairing, there's a component in there that as the train passes over the bridge, there's a series of layered plates. And the Sioux actually went back in the 80s and replaced those plates with stainless steel. But as the train goes over the bridge, it increases the friction on this plate and it actually locks up the structure right in the middle of the truss. And that makes the truss stronger, that makes that arch stronger. We have what we call a 3-hinge arch, which essentially has a hinge at the bottom, in the middle, and in each end. And that's very flexible, which is great because, like I said, Sioux line bridges like to sink. And this bridge has a pretty good low spot in it as well. The center of it sunk down probably a foot or two, though it's so long you can barely tell. But nonetheless, it has that flexibility to move and settle. But a 2-pinned arch, as they say, locks up and provides much more capacity. So it's interesting how the spans in this bridge are able to kind of convert themselves between two different types. It's a really unusual detail, I think a really innovative detail. It's pretty cool structure. And what I always liked about the High Bridge is for those that are aware of the whole situation out there, you know where the low crossing was that goes across. And I'm not a historian, I haven't read the story, but as an engineer, I can really kind of admire the person. Somebody walked up to about this spot and said, we're going straight across that way. Just straight that way. We're done with going down the hill and back up the other side. Just let's build it straight across. And that's what got built. And so that's why I truly am impressed with that bridge. All right. I think just to wrap up the end here, I do a little bit of modeling myself, HO scale modeling. And I was actually hoping that I'd have time before this to build something, and I'm still in the middle of my career, and I don't always get a lot of free time. And then to tell the wife, well, I know the railroad told I had to go to North Dakota this week, but would you mind if I spent the next 3 days building model trains? You get the typical response to that. Anyways, don't want to sleep outside that much. But I did think it was, I'd heard that folks that model may want to have some pointers or some discussion about modeling. And so I did want to talk about what I would call the Dakota Bridge. And the reason I kind of bring up this example is when I talk about the Northern Plains, those wheat line bridges on Northern Plains, DMVW, this is the majority of the bridges out there of this type of design. And it's I think a very simple project if you're modeling a bridge. It's a very simple project to do, and it makes a really neat looking bridge. And you can, especially if you're going to do a wheat line, you can do something that has a little bit of character that says, yes, this is a Sioux Line bridge. So the basic components it was all timber piles, and we have what we call a timber approach on each side, and then there's a steel beam span that would go across wherever the main opening is. You see a lot of these in Wisconsin would be over roads and over waterways, but in fact I think there's a painting over here that has one over a waterway, but nonetheless very common over roads as well, and more than other railroads than the Sioux would put them over roads, but this one is very common on the Sioux itself. So the basic configuration, you have those timber trestles on each side. They're typically 12 to 14 foot long spans, so you just kind of work that out in your particular scale. And then there would be a steel beam span that would rest across, maybe go across the main opening, whatever it was, the road or the main channel of the waterway. And you can see that the goal with that big span was to let junk go through there. You can actually see in the water down underneath there what looks like antifreeze again, the old pilings of the previous bridge. And those bridges catch drift, and you saw the pictures of the bridge in green where the drift was just pushing the thing aside, and the ice as well. And so having this big span in here allowed all that junk to flow through a little bit better. The spans are usually like somewhere between 25 to like 40 foot long. Evergreen plastics builds a lot of, if you've got basically a 3/8 inch deep I-beam that they make a model of, that'd be a 3 foot deep beam. And there's always 4 of those beams together, braced together about either what we call the quarter points or the fifth point. So you can see the braces between the beams underneath there. There's one right in the middle, and then there's one, it's a quarter point each way. So all stuff you can get, from the hobby store in terms of a 36 or be an HO scale. You're talking either like a half inch or not a half inch. I'm sorry, a quarter inch or a 3/8 inch deep beam. Build that pretty simply out of evergreen plastic. Paint it black. If it's over a road, you got to put the big Sioux Line decal on it. But if it's out here in the middle of the Dakotas over water, you don't need the Sioux Line decal. And the beams are typically spaced about 30 inches, so you just convert that to your scale. Those beams rest on what we call timber pier. If there's just a beam and a timber going one way, you're going to have it's basically 2 rows of piles, 5 to 6 piles each. Each of those rows of piles are going to be braced together, and they're going to have a 14 inch by 14 inch timber cap that goes across the top of those and frames those piles together. And then there's 14 by 14 inch by 5 to 6 foot long timber blocks running the same direction of the rail, usually about 8 to 10 of them across, that would support the beam on one side, and then stacked up a couple of caps on the other side that would support the timber going the other direction. So that would be where the steel is at. Everywhere else, you're just going to have a single row bent that would support the timber span. And like I said, you're going to have 1 or 2 caps that has to make up the difference between the timber side, the difference in depth from the timber side to the steel side. So the timber trestle, the Sioux had a pretty standard open deck timber trestle, very similar to the Milwaukee Road. And it's usually consisted of 6 10 by 18 inch timbers. They'd be grouped together in groups of 3. We call it cords. They pack them tight together in groups of 3. So 10 by 18, you're talking about something like 1/8 by 3/16 or something along that side, an HO scale. And they'd pack them all together tight and then rest on top of the timber bents. This little detail right here, how they actually held the timber stringers are going at the top of the photo, and there's our timber bent below. Those round bar straps that cross, that is a classic Sioux line detail right there. So if you want to make your bridge look like a Sioux line bridge from like about 1950 to about basically until the Milwaukee got involved, you're going to have those straps on all the bents in the middle of the bridge. The Great Northern used plate straps that were galvanized and had a whole bunch of lags in them, but they never used the round bar. Milwaukee used angles. They'd have an angle that went on there. And when the Milwaukee and the Sioux merged, that's right around the mid-'80s, you see those straps disappear and the angles show up. So I don't know, somebody decided that was a better idea. That would be in the middle of the bridge. So there you see the straps really well, the crossing straps. And so definitely a little detail if you want to include, if you're doing a Sioux line timber bridge, open deck bridge, you want to have those little straps there. If you're doing the deck, it was a microengineering, makes a great bridge tie deck material. I think Walters is building one, he makes some now too. But they're basically 8 by 8 by 10 foot string or ties. So if you're building it in a different scale, and they're about 1 foot on center all the way across there. And you want to make sure you have about a 4 by 8, 3 by 10, or 4 by 8, we call it guard timber or spacer timber on the outside, each side. That's to keep the ties evenly spaced all the way across the bridge and keep them from sliding and bunching together because there's no ballast on the structure. Finally, the bents themselves, I said a 14 by 14 inch cap. They're 14 foot long, almost religiously. The bracing material is all 3 by 10. And if you got over about 2-3 foot tall, you're going to have what we call sway braces that go back as an X. You get over 12-14 foot tall, you're going to have the sway braces plus a sash brace, and you just kind of repeat that process as you get taller. So, but it's always good to have the bracing on there. Timber trestles is important to show. At the ends of the spans, if you look at this right there, the Sioux, instead of the strap that goes across, they used a single vertical angle. So there's a little steel angle. You can see right where the steel beam comes in there, you can see a vertical angle on the going from the stringer to the cap. And that's how the Sioux did the detailing at the ends of their spans. So if you're looking to model that, your ends of the bridge are going to have that little single vertical angle on the outside going from the face of the cap up to the face of the stringer. And that's how they did the terminae of the ends. And then, of course, it's not a North Dakota bridge unless you have the icebreakers. And so you're going to want to have, on these small beam spans, there was 3 piles driven in a triangle. The 2 back piles basically line up with the rows of the timber pier, and there's a pile centered in the middle. And then it's usually like a 7 by 14 or an 8 by 16 timber that would be boat spiked or lagged into those vertical round piles. And then there's often just a round, they took a piece of plate steel and they rolled it and then lagged that to the timbers, and that would make the nose of the icebreaker. And that was basically just to defend that pier against ice coming down the river. And if you're having some fun modeling, you could have one like half crushed, because they did get destroyed on a regular basis. And so if you drop the model, then okay, that's what happens, just the ice. So. And then finally, I think another good thing is the lagging. And so if you have really bigger spans or taller bridges, you're going to see a lot of these. If you think back to those Oslo photos, we actually even did this in Oslo with steel. But they would apply timber lagging all the way down the face of the pier on the inside facing the river. And the reason for it is that the ice sometimes, even though it broke around the end, you could get around and hook the pile as it went by. And so they would put the lacing or the lagging up there, and this was usually just 6 by 12. It's a little lighter stuff, even 3 by 10. Put it pretty tight together so the ice couldn't find a way to get in and lock into things. But it's basically to deflect the ice as it went by. It would be pretty ragged and pretty rough. You could show joints in it, you could show sections missing. It does fall out every once. It does get knocked out and it has to be replaced. It was a maintenance item. So, all right. So, 8:41, I said I had till 9, so I think I'm doing okay in terms of time there. But that's basically the end of my presentation. I got 2 more photos of trains in them, so the locomotives. We did the whole thing. The RDC at least had some power. So then there's a Sioux Line hopper on top of a Sioux Line bridge up in North Dakota. So that fully qualifies. It's being pulled by a Northern Plains locomotive, but we don't have to see that. And then that's honestly a real Sioux Line train. That was in the 1980s. That's so you saw the photo looking down the International Bridge. This is turned around. The turntable is off to the side right here, and I'm apparently watching a train leave, heading west out of Sault Ste. Marie here sometime in the 80s. So I figured a nice caboose photo to finish everything up and go from there. So open it up for questions.
Could someone bring the lights up a little bit?
Sure.
You know where they are?
I do have a lot of photos in here on this computer, so I don't know what that's all about. So if there is a specific question, I may even be able to find a photo of something, no guarantees.
Yeah, is there use of drones these days?
Yes, drones are becoming more common in the railroad bridge inspection world, and they haven't quite found their place yet in terms of what it's going to look like. You know, a lot of railroad bridges are really small, and so I think, and I know the model railroading community and the rail fan community, they like the Arcola Bridge. They like drama. That's impressive. Most railroad bridges are like 15 foot tall and 80 foot long, and I can walk through one of those and see everything I need to see just on the ground. So there's not much use for a drone there, but definitely with things like the Arcola Bridge, they're doing more and more in terms of recording. The biggest problem right now is you got to get in close to see a lot of stuff, and so a lot of the drones that can really do the work, really videotape everything and do the LiDAR and all that fun stuff, they're $150,000 drones, or even $70,000 drones. And then you say, can you take that and just fly it right into that piece of steel and see if that's what we, they just, no, we don't want to wreck our, there's a debate whether we, do we just buy like 50 $200 drones and, well, that one's done, I'll try it again, see if we get a picture. I mean, and I'm not saying that's the, other than the litter aspect, that might be the best way of doing it, but it's definitely coming. I think, one of the things I thought another gentleman I do the bridge inspection class with, we thought would be a great idea is if you could basically have the drone go through, and especially with like a bridge settling or moving, to have the drone go through and set up waypoints, physical benchmarks that are fairly solid. The drone goes through, does the LiDAR, says, okay, this is where everything's at, and maps it all for you, and has that point cloud already mapped. And then the next year you go out and launch the drone, it already knows what path it's supposed to take. It goes and does its thing. It measures the bridge, it ties it back into those physical landmarks and says, this part's moved, this part's different. These things have changed. And that's difficult as a bridge inspector to go through a bridge and try to perceive change year out, year in, especially really slow movement, settlement. And that's, I think, where the drones will do a great job.
Last few years, you've been working on it. Have you ever done any work at Gill's Landing at all?
Gill's Landing? No, I've avoided Gill's Landing, thankfully. Yes, the gentleman I work with, the bridge inspection class, he was a CN structure supervisor, and he's had a lot to do with Gill's Landing and the hydraulic raising system there and everything.
Because last week they had a lifter bridge to let a houseboat go through, and it took, I think it was either a 2 or a 4 hour window they had to do to get the rails back in again. And
yeah, it's one of those things that, as a railroad bridge engineer, I'm a consultant, so I don't work directly for the bridge, but there's, through all the short lines, I'm responsible for 400, 500, 600 bridges. And a lot of these supervisors on the railroads are responsible for thousands of bridges. And something like Gill's Landing is just really tough because, there's somebody that wants to run their boat through there every year, and there's all this effort and focus on a structure like this when you have other structures that you really would want to pay a lot more attention to, but you have to focus on something like that because someone wants to run their houseboat up there. And I'm not going to get way too far into that, but yeah, it's designed so that it can be raised every once in a while, get to go through and close it back up, and that's about it. Let's do it.
When you have those timber trestles and they backfill those, how does that timber hold up over time?
Like when they bury them?
Yes.
It holds up remarkably well. So, in fact, I remember one aspect I remember in most soils is I went to Michigan Tech, and up in Mason, there's the old Quincy and Torch Lake, and the Quincy had their big mill up there. And when I was up there, a box culvert had failed up behind that mill, and the stamp sands had all flushed in and like that, and it exposed a timber trestle. And knowing the history of it, the timber trestle was probably 140 years old, and it was, you can still see all the bracing. So, and this is Railroad Bridge Inspector here, so I'll try to make it brief, but timber decay is a fungus. And so timber decay needs, that fungus is an aerobic fungus. It needs oxygen in order to decay. So in fresh water and in dense earth, you have less oxygen, the decay works a lot slower. So, for instance, where those big trestles are buried out there in North Dakota, chances are if you're really bored and you dug all that out, it'd probably be pretty close to what it was the day that it all got buried, because it's been deprived of oxygen and has very little chance. It's still decaying, but it decays much slower basis. So, all right, I'm going to move to the middle. How about there?
On the Dresser subdivision by Osceola, the swing bridge that you put the concrete girdle around?
Yep. I didn't know if I was going to get the tomato flying at me.
Talk to me about the juju on that bridge.
Yeah. The stone falling off that. Yeah. I haven't had a whole lot of experience with that bridge. More question on it, or just, I'm sorry.
Well, I want to know your juju on it. I'm going to go over that bridge next Saturday.
Oh, well, it's doing better now. It's all encased and it's in good shape. I don't have a whole lot of experience with that particular bridge outside of that encasement work. The one thing about that, you have a rail line that's used by a tourist railroad and a competing railroad for their ballast, and nothing for your own customers. So you think about how much a railroad wants to invest in that. It's our competitor's ballast source, and it is, after the whole KCS thing, we might not even be in a friendlier mood about that. And then it's this, it's the short or the tourist railroad. So, they do what work they have to on it, but the CN obviously it's not a focus for them. But they did put in, it was quite a bit of money to encase those piers and stabilize it. So I mean, they take their responsibility towards it very seriously. But overall, from what I know of the bridge, it's a pretty stable, sound bridge. I believe the stone, and I think that was what the finding was from Eden Hunt. The stone is from the when I went out there in 1887. It's the original stone. The truss, the superstructure, the swing span, I think it dates, it's after that. I think it was more like 1905, 1910. It had very similar dates to the big bridge, the Arcola Bridge. It was confusing because those two files got mixed in the computer database for all our bridge plans. So we thought, I was looking at the big arch bridge, and it was actually parts for that swing bridge. And then I believe the one end of the bridge in Osceola was replaced in the 40s. Those concrete piers you see on the Wisconsin side are all newer. And I think there's even something similar in there. So it's probably, I wouldn't have any problems riding a train across that bridge. How about that? All right. I'll go over here.
Great presentation. All your photos and your documents that you have, I would love to see the society have access to that. If you get to places and bridges that we would love to be able to get to as a modeler, and all your points in the whole presentation I saw as great article potential. I would love to see that stuff get published. To get
Cartoon.
To say this.
Cartoons, yes.
That's all that was just a couple.
He made a joke about cartoons because when I was at Tech, I did cartoons for the paper up there, way in the back.
How much vertical deflection is there in the wooden spans when a locomotive goes over them?
Well, a properly supported one, maybe on a 16-foot span, maybe quarter inch to an inch, depending on condition. And it depends on how fast they're going. But when I talked about the green bridge and flexibility is the key to success, that's how timber bridges really get it done. So one of the things I'd say about if you're around a timber bridge, and especially if it's any speed involved, so if they're doing 45 over a timber bridge and you see that thing dance all around, I would not get too worked up about that. The key thing is, if it dances all around when the train's going over and at the end of the time it goes right back to where it started, that's perfect. That's all we want to see. I've watched, I remember quite a while ago being out on, it was at the time the Chicago Central and Pacific, the old IC line across Iowa, it was over by Council Bluffs. And I watched a loaded coal train go across a timber bridge at 45 miles an hour, and I'm absolutely sure the timbers were jumping up and down probably 1.5 inches, 2 inches. But when it was all done, it all settled right back to where it was. And that's what timber bridges do best. They're flexible. Any other questions?
On the longer steel deck bridges, or steel truss bridges, one end is anchored to the concrete. The other end is, the ones you see, are they on roller nests, or they're bronze plates, or what? Just for the
Structures
temperature.
101.
Yes, the expansion bearing, which on every railroad bridge is used and often failed. No, it's an expansion bearing. So yes, you have to have, basically the rule of thumb is an inch per 100 feet per 100 degree swing for a steel span. So if you have a 100-foot steel span and the steel goes up 100 degrees, the whole span's going to grow about an inch longer. And steel can do even more than a 100-degree swing because the steel itself gets a lot hotter when it gets sun on it. Yeah, they do have the expansion bearings. There's a lot of different variations. The Sioux, once again, was probably a little bit on the cheaper end. So any of the older bridges, if it was less than 100 foot long, probably just had 2 sliding steel plates. It just had a slotted hole and a steel plate, and that was it. The anchor bolt on that side, there was a slot around it, and it would slide back and forth, just steel on steel, which is reasonably effective and actually completely allowed by the engineer folks up to about 50 feet. So beyond that, they have rollers, and then sometimes they have rockers. They have rockers, and then the bronze plates that you talk about, and there's Teflon, stainless steel stuff we use these days. That's probably something you'd see after World War II, less common.
For those small bridges, why don't they just replace them with culverts?
Well, that's flooding. So, I guess at one point I alluded to the fact that, on the Sioux line, if I see a bridge, I know there's supposed to be a bridge there. So, before we all had D10 cats and big scrapers and everything like that, the best earth moving equipment we had outside of the train was, I say, horse swims and Irishmen. The fill in a bridge back in 1905, you either used the train to fill it in, or you had to have a whole bunch of Irishmen and dig a bunch of stuff around. So when you built a railroad, you often built a timber railroad first. You built bridges, and then you decided whether or not you wanted to keep the bridge. And so they built timber trestles because the best earth moving equipment was that train. So let's get the trestle there, then the train shows up and it can side dump all the dirt up and fill the hole. Some railroads, like the Chicago Northwestern, just kept the bridges. I don't know why, but they didn't feel like filling them. The Sioux line, they went back through, and in the early parts of the 20th century, 1910s, 1920s, the whole science of hydrology, and we call it H&H, hydrology and hydraulics, basically figuring out how much water is going to go through a particular river or creek and go through our bridge. That really blossomed around then, and the railroads figured out, okay, this is how big of a structure we need. We can put a culvert in here. And the Sioux line did a very good job of doing that extensively through their structures, and if they didn't feel there needed to be a bridge there, they would put a culvert in. So there's lots of culverts on the Sioux line that have, there's...
Modern precast concrete, you can make some big monster culverts, replace these, and be done with it.
Oh yeah, you could. But a timber trestle, the timber trestles in these photos, a lot of them are built, like the Sioux went through and built a lot of these things back in the 60s. And almost all the ones you see on the prairie lines out here were built after 1960. So they're all fairly new timber trestles. They're working, they're doing their job. So it's an asset, it works, it's sufficient for the trains. I'm going to keep that timber trestle in there until at such point it doesn't do its job. And when it doesn't do its job, precast box culverts are definitely an option. We do steel spans. The thing about a box culvert is it may, sometimes they're just more expensive to put in than a bridge.
Well, you've also got to do with the hydraulics of your you're taking the stream bed and you're bringing it in against a solid deck. You've got to deal with pressure on and the hydraulics on the end walls. So there was an interesting scenario on this when I was still working in the engineering world, was when they were going to try to take and extend Amtrak from Milwaukee to Madison. It was on the Wisconsin Southern. And the initial plan was that they were going to take all the old timber trestles, because it was very light traffic, they could interrupt traffic for a couple of days. And they were going to pop these trestles out, and they were going to plop in all these prefab box culverts. But the reality is you got to have the foundation right underneath it, or the box culvert doesn't do any good at all. In fact, it creates more surfaces that can be attacked than the timber trestle.
Yeah, and another reality is that if you're talking to the dispatcher again, hi, I'd like 12 hours to put a box culvert in. Go away. When I showed you the picture of the Manitowoc Bridge, and we figured out how to fish piles in around all the existing steel and all the existing piers. And that's really what a railroad bridge engineer, that's a big part of our job, is like, how do we build the foundation for our new bridge without, it's like open heart surgery. I got to keep this old bridge alive and beating while I put in the new bridge. And as it turns out, bridges are actually more conducive to that, because you can drive steel piles in between locations or around the bridge a lot easier than it is to get a box culvert underneath them. And these box culvert, like a 10 by 10 box culvert, or a box culvert, weighs 45,000, 50,000 pounds. It's not easy to pick up with any piece of equipment other than a crane. You can't just pick up like an excavator and shove it in there. And so it becomes a lot easier just to drive the pile in between and then get that 3-4 hour window, and all you have to do then is take off the top of the bridge. You can leave all the old timber pile in there until after you've put in your new span. You put in your new concrete span. They are concrete spans we put in, precast concrete spans. And then all the old timber or whatever underneath gets wiped out sometime after the span. And the nice thing about the concrete spans is we can do like 30-foot spans, as opposed to really a railroad box culvert, precast railroad box culvert really kind of tops out at 10 foot. They make 14-footers and stuff, but they're a special beast, and they're really getting heavy really quick. So, the precast spans are very effective. And I've had to price both. In fact, actually, not too recently, we had a job we went out to bid as a precast box culvert, and it came back so high, and we went back as a bridge, and the bridge was like 30 grand cheaper. Not a big difference, but like 4 or 5% cheaper than the box culverts. Oh, good.
What is the differences between open deck and ballasted deck as far as the structural loads on the bridge? And do you have a feeling of which is better? And do they typically use guardrails on a ballasted deck?
Right, so, it's a...
Let me answer this question in 97 segments of 5 questions each.
No, this is, and first of all, I don't know if anybody knows the difference. We were talking about this picture of this bridge behind us, an open deck. So an open deck is you have the structure of the bridge, and the ties rest directly onto the structure of the bridge. A ballast deck bridge, we build a trough out of wood, out of steel, out of concrete, and then we put ballast in there, and it's the standard track section through there. So they have pluses and minuses. An open deck bridge initially is cheaper to build. It's lighter. The weight of the structure is a lot less because you don't have the ballast in there. I make a little corollary. I say that if you have a bucket of ballast, the ballast is going to weigh more than the bucket. And the same thing's true with a steel ballast deck bridge. The ballast on the bridge is the heaviest thing there. It's a lot of weight to put on the bridge. But it does dampen the force of the train as it goes over the bridge. So actually the engineering folks, the ARIMA, the people that basically set out the recommendations for how to design a railroad bridge, they say if you have a ballast deck bridge, you can actually reduce the amount of impact that you designed for. And that's the force of the train slamming onto the bridge and leaving. So if you parked a train on a bridge, you'd do so much damage. If you ran the train across there at 70 miles an hour, it's doing a lot more beating up. And for the ballast deck, they give you a little bit of bonus because it basically is a shock absorber. So the advantages on the ballast deck side is they reduce the impact load on the bridge. They're great for surface. So the equipment that you use off the bridge, you just run it straight across. So the tampers, pretty much the regulators, all the track maintenance equipment that works off the bridge typically works on the bridge, especially for maintaining surface. So you can tamp right across it. So if you're riding on the train, a ballast deck bridge is going to give you an excellent ride. And it's going to be much easier for the track crew to maintain. If you want to raise a section of track 3 inches, do an out of phase we call track raise, on a ballast deck, you just go right across the bridge. If it's an open deck, I have to go back and shim underneath every span to raise it up 3 inches. It takes a lot of work. But an open deck is easier initially. It's easier to build. It's cheaper to build initially. They're a little nicer on all the structure underneath because they are open and then things dry out. So like on steel bridges, ballast decks, you have moisture, you have just material in the ballast that over time seeps down through and causes stuff to corrode and stuff. And that you have a lot less of that on an open deck. And I think one of the last things is an open deck is thinner. So if you're over a road and you only have so much room, or if you're over a waterway and you have to keep your structure as thin as possible, an open deck will allow you to have a structure that's maybe 2 feet deep, whereas a ballast deck, you're going to add another 8 inches to that because you have to have room for the ballast. So it's a debate. If I was in a room full of a bunch of bridge engineers, we'd all have, it'd be 35 one way, 40 the other way. I mean, it would be a fight on whether or not ballast deck is better or not. But they both have their uses.
Great presentation.
Thank you very much. Thank you. You want me to block it out?
Okay, thank you, Peter. That was a very informative talk, and I actually learned a lot about bridges, and I had just built a timber bridge on my Sioux Line layout, so
hopefully you don't have to tear it all out and redo it.
I can tear it out and build it over. No, it was very good. All right, we're going to take a short break. What time is the auction starting? Does someone? All right. So it's going to start as soon as we're ready. We have a treat this year. Emory had a prior obligation, so we have Jerry Wojo. Where are you, Jerry? There he is. Who's going to be our auctioneer? So we're going to have a lot of fun.
Spend lots of money today.
And I hope you have big, bulging pocketbooks full of money this year. So we'll start as soon as we get a chance. Thank you.